click Start Record.
All right. So just let us know when you want us to start.
Yeah, I'll do just a quick intro, and then I'll turn it over to you guys from there. So you've already got your slides loaded, and we should be good to go.
So Adam, if I make it full screen, then it shows as full screen for all of you, or how does it work? Do you have any idea?
That's a great question.
I think it's up to the individual user how they display it on their screen. I don't think it matters how it's on your screen, as long as what's in that window is what you see. That's what they're going to see.
Okay.
Well, I've got 1 o'clock, so let's get started. Welcome, everyone, on behalf of the Kentucky Transportation Cabinet, Federal Highway Administration, and ACEC Kentucky to the 2020 Partnering Conference Day 2 virtual session. If you're looking for the general planning track, you've come to the right place, Jack. Got a whole host of very good topics and presenters this afternoon. And beginning with a session on microsimulation parameters. With us today from the Kentucky Transportation Cabinet and Division of Planning, we have Jay Balaji. And then from HDR, we have Adam Hedges and Rob Frazier. So with that, I will add that if you would like to ask any questions, we should allow a little bit of time for that at the end of the session. Use the Q&A window. For those of you that maybe weren't in the sessions yesterday, you click down the bottom right of your screen, you just see options to join the chat window. So there will likely be some ongoing discussions throughout the session. You click on the Q&A tab, though, you can ask your questions as we go, and we'll try to address as many of those as we have time for at the end of the session. So with that, I'm going to turn it over to our presenters, the experts, and we'll take some questions at the end. Thanks.
Thank you, Brian. Good afternoon, everyone. Excited to be here, even though I cannot see any of your faces. Since Brian already told the housekeeping rules, how to enter your questions, you can ask your questions throughout the presentation, and we will try to answer as much as we can within the time frame, but we will try to address all your questions as much as possible. And to begin with, I would like to give a brief overview or history of the project, where we started and how we got here. If you're familiar with microsimulation softwares, then you know almost all of these softwares have default values for parameters that cannot be easily captured in the field. Or you can say that you can capture it, but it takes a lot of time, money, and effort to analyze those parameters. So I love how all these softwares, even those softwares that were created in different countries, have US-specific default values, but we live in a vast country with a lot of different driving behaviors, beginning from driving behaviors or terrain and level of condition. It's different between different states. And if wouldn't you love if we have a state-specific default value for these parameters that are unique for your state? last month, the same time, I was driving my daughter to Philadelphia to drop her off in her college campus. Um, that place is called University City. The name is due to the reason like there are like 6 or 7 universities in there. So you can imagine the student population in there, like thousands of students. And what is their mode of transportation? Can you guess? If you have guessed it is walking, then you're right. You get a point for that. Students, they are pedestrians, they walk to their classes, they walk to their lab. And if you have like many universities at the same place, you can see how much pedestrian traffic those kind of areas get. So I was driving in a one lane road near University City, and I saw a pedestrian on the road crossing an intersection. And usually, what do you do when you see a pedestrian in Kentucky? You just slow down and let them pass. That's what I tried to do. I slowed down my vehicle and I heard all these honking noises uh, behind me, and a lot of drivers, they were losing their patience and they were swerving on the opposite side and cross the intersection. So these difference in driving behaviors, when you're able to capture them, and these differences, they have a huge impact on your output in a microsimulation model. And that's why we need to capture all those differences in behavior, driving behavior. And there are several other things that needs to be calculated too. So our cabinet, it determined that a guidance document should be the first step in addressing this need. And this documentation, it will provide a foundation to build upon, and at the same time, it can provide a statewide consistency in standards also. So we started this project in late 2018, and we divided this into 3 phases. The phase 1 of that project, I consider that we achieved 3 important milestones during the phase 1 of this project. It was done by Kim Lee Hon and HDR. The first important milestone is we were able to analyze all the documentation that was done by similar kind of documentation that was done by the different states, and to analyze what the recurring themes are, and to take an inventory of national level best practices that were followed by these other states. So that was one important thing that we did in phase 1. And then the next milestone was a development of a software selection tool to help the project managers to determine what kind of software they need for their project. This tool had like series of questions which the project manager can answer, and it will let them decide, do they really need a model for their project? If they need a model, is it a micro simulation model or a macro model? And then when it says micro simulation, then there are a lot of other options too, like if you need a synchro model or a Vissim light or Vissim, or it gave you several options to pick from, but it also let you fine tune or minimize lot of options that are available for you based on the answers that you give for your project. And the third important milestone was we had a technical advisory committee meeting at the end of the phase 1, for which we invited all of our pre-qualified consultants from planning, highway design, and traffic op, who were qualified to do modeling work with KYTC. And then we invited all of our MPOs, and then our software companies like PTV and Caliper were also in that technical advisory committee meeting. And the main idea of that meeting is to gather input from all these individuals what they want to see in the document, what they because at the end of the day, they will be the user of this documentation, so their input, we thought it was very essential for this, for us to do, to cover everything that was needed for this documentation. So with that, from the phase 1 analysis and the TAC meeting, we finalized that there were 9 parameters that we need to look into in the phase 2 of this project. That's where we are in, and that's what you will be seeing today, the results of the phase 2 of this project. And we are planning to wrap the phase 2 of the project at the end of this month, and then the phase 3 will be the guidance documentation and user training, and that will be done by end of January 2021. And before I hand over the presentation to Rob and Adam, I also want to thank that Jill Asher and Scott Thompson, they initiated this process and made it possible for us to bring this guidance documentation to all of you. And with that, I will turn over the meeting to Rob, and he will tell all about the work that they did for the phase 2 of this project. Thank you.
Hi, thank you, Jay. I'm gonna give a little bit of an overview here, just to kind of keep getting us headed in the right direction here. So I just want to, at a high level, make sure we're all on the same page with what this project is all about. It's all about microsimulation guidance that is based on research and Kentucky-specific data, and so that's a very important part of this. Is Kentucky, and Adam's going to go into this quite a bit. So we're going to go through these fairly quickly. The purpose is to look at establishing these standards for microsimulation, and to improve how we're doing our development and validation of models. And then tool selection, which Jay mentioned. So that's kind of the purpose of the larger project, all 3 components together. And the next slide, just kind of importance is to look, improve. We develop very good and accurate models, but we want to keep making them better. And now that we have more data that is Kentucky specific, we can make them better for projects that we're doing, data-driven projects we're doing here. So that is that's kind of a theme. And then finally, the innovative piece of this is kind of looking at developing ranges with some of the data. So let's move on to the next slide here, Adam. The 3 types of models: macro, meso, micro. Macro is often statewide or national. It can be a region, but it's a big area typically. And so, region, state, nation. Meso looks at a portion of that, maybe a portion of a region. Maybe it's a large downtown area or something. But micro gets down to the individual vehicle and person. And so that's really the focus of what we're doing here. And so we've got a polling question at this point in time. We just want to find out. I'm going to go ahead and hit start polling, see how this works. We want to know, of those of you who are with us today, how many would classify themselves as an expert user, a standard user, novice user, or no experience. And our goal here is to serve everybody. We want to help with making sure, if you're a project manager, that you're scoping it correctly, in the best way. So this project's about helping everyone at all levels, but we're just interested in kind of who's in the audience today. Give you another second. I see people still. All right, looks like that's about it. So, Adam, it looks like we've got about 16% experts and a quarter standard, about 40% novice, and around 20% no experience. And I know that didn't add up to 100. I didn't round all the numbers. So we'll go on to so that's kind of the audience that we have today. That's great. Let's go to the next one. And so the what, when, why, and how. I'm going to scroll through that in the next few slides here. So the what of microsimulation, I was mentioning it's individual level of each vehicle, even down to people or buses, trucks, can be any anything that moves, and as well as people on bicycles. And so we want to look at the characteristics and behaviors. I know, keep going, Adam. That's great. And look at the characteristics and behaviors of how they operate. And the why and the when is often it is to help us make planning and design decisions, to answer questions that are operational questions, such as will a particular weave or merge work, or how does an intersection work? Does it need particular turn lanes? And often it's used when there's some complexity or unusual situation. So it is not generally cost effective for just your run-of-the-mill work, but it is very important when we're making sometimes important decisions or decisions that involve ultimately a lot of construction dollars. So the next slide is kind of the last piece of this is how do we do it? Often we're using one of these two pieces of software, either Vissim or Transmodeler. And we actually have a follow-up question here. Thank you, Adam.
Yep.
So give us a quick, we should have done both. I realized too late that we don't have both on here, but just pick the one you use more if you use one of them more. And we'll see. Adam, we'll let you're tracking this one, so.
Yeah, I'll give it another second.
So these are generally the two packages. There are several others. Corsim is occasionally still used once in a while, not too often anymore. And then there's AIMSUM and others, but these are the two most common. And really our guidance is aimed at these two. At this point, it's not just for these two. You could apply it to others, but we want to make sure that if you're using one of these, you've got the information you need to get started on a model in Kentucky.
So the results are about 50% of people are using Vissim, 30% are Transmodeler, and 20% are other. So.
Got it. All right, let's move on then to the next thing. And so we're capturing most everyone with what we're doing here. So this is a quick rundown. It's the same slide that Jay showed before, but with a little bit more information about each of the phases. And I'm going to just touch on a couple of things in phase one on the next slide here that I want to just touch briefly on. That one of the things we did is to look at what other states have guidelines. That's the map there. The states in red have guidelines. Ohio, Kentucky developing guidelines right now. There may be others that have, since this map was created, that have been working on them. This is, I think it's going to be valuable for anyone that's doing this kind of work in Kentucky. And I will mention just here, we are actually working on having some files that will change. For example, if we propose to change the default, we want to be able to give folks a file that they can start from. So we want to make this as easy as we can on all of us who are doing this kind of work. And then the second thing I want to point out is we did some model development best practices already. So in phase one, we actually wrote a piece of the guidance document already that goes into how best ways to code models as you're setting them up. So that is some of the stuff that's in phase one and is getting rolled into ultimately the guidance document that we expect to have a draft of by the end of the year. Next slide goes into we're going to start getting into the kind of the meat of the presentation at this point with how when you drive, think of you're out driving, what are the factors at play in how you drive? What are the things that affect how fast you're going and various things? So your vehicle has certain characteristics. It has a maximum acceleration. It has a size. The environment. There's weather. There's time of day. There's other vehicles, and those vehicles interact. Maybe there's a truck in front of you. You want to give it more space. Maybe Maybe you could be an older driver, a younger driver, and you may have a different driver behavior. It's another whole category there. And so all these things affect how we drive. And the next slide shows how we try to capture many of those in the model. And so in the model, there are vehicle attributes and acceleration and deceleration. There are driver behavior characteristics, and there's lots of those. Humans are complicated, so there's a lot of driver behavior issues there. And then there's speed profiles that affect the range of speeds that a vehicle is going, say, on a 55-mile-an-hour road. There are link attributes for how you drive a piece of road when you know you have to turn up ahead. When do you get into the right lane? So there are all these different things, and Adam is going to pick up here, and all the ones that are highlighted are really the parameters that we have focused on in our work, and they're key parameters that affect how the models function. Adam, with that, I turn it over to you.
Okay, thanks, Rob. Yeah, so as he mentioned, kind of the highlighted ones there are the ones that we're looking at. There are really 9 key parameters that we're going to be discussing and that we've tried to develop values for. But a main piece of the phase 1 work leading into phase 2 was identifying the parameters. We just popped up on the screen like 20 different things. So identifying which ones are important and which ones we think we can impact. So we selected them really based on them fitting into one of these 3 criteria. So parameters that are frequently changed, parameters that have significant impacts on models, whether they're often changed or not, and then parameters potentially have default values that are significantly different from Kentucky values. So those are really the 3 criteria that we were using. And then from that, we determined these 9 parameters to be the ones that we thought we would study and try to develop information for. So I'm going to turn on this drawing tool so that I can not talk with my hands as much, but these are the 9 parameters. I'm going to try to run through them here pretty quickly, just giving an overview of what they are, and then I'll kind of follow back up on each one to go a little bit more into the weeds. So as you can see, just in this list here, so time headway is really the spacing you're leaving between vehicles when you're driving. So just the kind of the air gap between you and the person in front of you. Minimum headway is how close you're willing to get if you have to make a drastic lane change or merge or weave maneuver. So not what you're trying to do, but your tolerance for how close you will get. Then we have acceleration and deceleration, which I think everyone is familiar with, just how fast you're increasing or decreasing your speed. Standstill distance, which is just the representation of the spacing you leave when vehicles are stopped. So in congestion or at a stop sign or a stoplight. And then lane change distance, which Rob alluded to, just the distance before an exit or a turn when a vehicle will start to get into the correct lane. So if you're in the left lane, you need to take an exit on the right. How far in advance do you get into that lane? Vehicle speed ranges, which is just the distribution for a given speed limit of the vehicles on the roadway. So you have 65-mile-an-hour roadway. Is everyone doing 65? Are some people doing 70? Are some doing 40? And anywhere in between. And then vehicle fleet composition, just the makeup of what types of vehicles and percentage of heavy vehicles are in the fleet. And then the final one was the truck weight to power ratio. I didn't have an excellent graphic for this, but you get the idea. It's just the trade-off between weight and power for heavy vehicles, which impacts their acceleration and deceleration and effects on curves and grades. So before I dig into the parameters and the analysis that we did, I just kind of wanted to hit on the way we were doing it. So there's kind of 4 main different analysis methods we were using: historic speed data analysis, VIN data analysis, and then just kind of some research documents. So those are kind of the three more traditional ways that you would see someone do this. A key way that we're trying to investigate these parameters, and you can see we're doing using trajectory for 6 of the 9 parameters, is doing that, doing trajectory analysis with Kentucky-specific traffic data. So we use drones to collect traffic videos at 8 different locations so far throughout the state. So some in the Louisville area, some in Northern Kentucky area, and some in Western Kentucky in the Paducah area. So we're capturing urban and rural environments and arterials and freeways. So just because that's a different piece of this, I wanted to hit on that. So again, this is we're looking at real-time vehicle interactions with kind of at an on-demand level. So this is a screen capture of a video that we took in, let me change this color, a video that we took in Paducah, and you can see this intersection is the same intersection that's in this. So this is the video data. We upload it to a platform called Data from Sky, and they're able to track each vehicle as they're driving through the video. And so the vehicles are geo-referenced, and you can get things like speed, location, acceleration, deceleration, headway, a bunch of those characteristics. They're a little harder to decipher than the way I'm making it seem, but you're able to get all of that in the video. And then from there, we're kind of exporting that data into Excel or another data platform to do the analysis. So yeah, again, the company is just called Data from Sky. This is a PDF, otherwise this would be an animation, but you can see even here in this roundabout, they're capturing each vehicle, and they're tagging it with an ID, identifying what type of vehicle it is, and different attributes, so the speed or the acceleration, things like that. So this is a new kind of realm of traffic analysis that I hadn't previously used, and I think it's going to become kind of a more popular way to do this. It is relatively inexpensive if you're going to be able to collect video data. I think they can do stuff with kind of MyoVision cameras, but also drone data. So it's just a kind of more detailed look at data that we previously have tried to examine from just a tabular format. So now I'm kind of going to run through each of these parameters. I would like to stay at a relatively high level. There's a lot of data and number crunching that is certainly interesting. I mean, I did a lot of it, so I'm interested in it, but we don't really have time. And but I wanted to just kind of, before getting started, give you a frame of reference for the slide layout. So each slide is going to look pretty similar. The main information is going to be over here in a graph or picture on the left, and then some more detailed data, if you're interested in that, is going to be kind of listed out on the right. So kind of what the parameter is, sorry, how it impacts models, where does it come from in the software, analysis, like how we did the analysis, and the data samples, as well as our findings. But I'm primarily going to speak to the graphic on the left. So just as we're rolling through these, I just wanted to kind of give some perspective. So the first one here is time headway, which I mentioned before, but it's really the time spacing you're leaving primarily on freeways between you and the vehicle in front of you. So how are vehicles doing that in the model? You can see here that our data that we collected kind of shows that most people are leaving anywhere from 0.5 or 0.6 seconds to 1.8 or 1.9 seconds. It's just kind of where the bulk of the data sample is. And that kind of lets the default value fall somewhere pretty much in the middle of that range. So what we kind of ended up recommending was a set of a range that really encompasses that 0.7 seconds to 1.6 seconds. That would allow you to use that in your models when you need to differentiate from the default. it is allowing also in the future, the current version of Vissim and the following versions allow you to input a distribution. So if you wanted to create an aggressive distribution, you might create something that is over here. And if you wanted to create a lower capacity scenario, you might be creating something that has values in these ranges. So creating a suggested range doesn't preclude you from using this default value, but really kind of gives you a upper and lower limit of what's a realistic value to try to use in creating a model.
So Adam, I think we've got a polling question for this. I just want to see where people fall compared to the data. So I've started the poll, and a question: how much space do you typically leave between yourself and the vehicle in front of you? So just think freeway. You're driving or some kind of interstate, parkway situation. So you know it's a 65 or higher speed limit. Right.
I think people are still answering, but it seems like most people are in the 1 to 2 or 2 to 3 second category. Somebody is a little bit more aggressive in the less than 1 second, but yeah, I found this parameter interesting when we were investigating it. I think when I was learning to drive, people always said that if you saw the car in front of you pass a sign or something, that if you were within 2 seconds of that you were following them too closely. It doesn't seem to always be the case, or doesn't seem to be the way that people drive, based on both the answers here, the way that I drive, and the results kind of from the software. So
yeah,
I'm going to move on to the next one here. So the next one is,
we won't ask who the one person is who said less than 1 second.
it's anonymous, yeah.
It's anonymous. Yeah, we have no idea.
But
Adam,
also don't drive with me. Yeah.
there are a few questions in the chat box. Do you want me to read it?
Yeah, I can try to look at that.
Why don't we just wait and hold those to the end, and then as time allows, we'll try to go through all those.
Okay.
Okay, that's a good idea. All right, so I'm going to move on to the next parameter here. This one is minimum headway. This is similar, but it's really the spacing. If you have to make a merge movement or weave or diverge, like how close are you willing to get? The default value is 1.6 feet in Vissim, which seems dangerously close, really. But from our data set, you can see we have a couple values down here at the bottom end that are in like the 1.5 to 3 foot range. And similarly, if you look at the Transmodeler defaults, theirs are based on time. You can see that our values with this blue line versus the Transmodeler values with this green line. Transmodeler ends up being overall a bit more conservative here on the upper end of this distribution, but our data is pretty similar to both Vissim and Transmodeler for minimum headway. And so this is a parameter we're actually just kind of validating what the software defaults say. Changing this doesn't have a huge impact on overall model performance just because it is not enabled that often. You do see people change it, and it was just something that personally I thought would be good to investigate and come up with some ranges for. So the next question, the next parameter, which we do have a polling question for, which we'll throw up here in a second, but is acceleration. So we're really looking at two pieces of this. There's a larger set that we could examine, but we're really trying to define what people are doing on specific roadway types based on the driving behaviors. So there's a standstill acceleration and acceleration from 50 miles per hour. And you can kind of see the data in the graphs are much more conservative and left-leaning than the actual data. But yeah, I guess if we want to put up that poll question, how do you accelerate?
How do you accelerate? Aggressive, standard, relaxed, slow? Yes. as Adam's about to talk about here, the data we collected kind of shifted to the left on the graph, slower.
Right. So our data is slower in general than the default values. The default values are from a standstill, 11.5 essentially. The highest value that we recorded was 9.2. And then from a 50 mile per hour standpoint, it was 4.9 to 4.4. So these are more similar, the default value and what we collected, but yeah, based on the Kentucky data, and some of this is due to other extraneous factors, so platooning, vehicles in front of others, things like that. So the maximum value is really what we were looking for, I think, there. Seems like most people are identifying themselves in the B or C category, standard or relaxed acceleration.
But not a small number of aggressive.
Right. So yeah, we're proposing to tighten this value down slightly to make it maybe more realistic, but not to overly tighten down the value, either of these values. So I will kind of move quickly through deceleration just based on time. I think everyone understands what deceleration is for the most part, just how quickly you're stopping or slowing down. We had a poll question, but I think I'm just going to keep going. And if you look at this graph, this is kind of our 50th and 75th percentile deceleration data compared to the Transmodeler normal deceleration curve, which is this green curve here. And then our data are these two blue curves. They're pretty similar. They're actually really close across the different speed ranges. So we didn't really, at this point, see a need to change the Transmodeler curves. Now, the Vissim curves, again, looking at it in a different way, these softwares just interpret the data differently. So I'm often showing two graphs just because to get it to be apples to apples, that's the best way to manipulate the data. So looking at the Vissim defaults compared to our deceleration curves, our data, again, is this blue and purple line. And then these Vissim default values are crossing the lines at kind of some key percentile areas. And so our recommendation is to really use those percentiles for kind of the accepted acceleration, deceleration, the deceleration that you'd use to allow people to change lanes, and then the maximum deceleration. So using kind of these ranges and providing some values and maybe a default set that's in the middle of each of these ranges will not vary the data too differently than Vissim and provide people with a real set based on Kentucky data. So kind of jump to the next one here. So the next one is standstill distance. Sorry, I was looking at the chat really quick, but standstill distance, again, is spacing people are leaving and stop conditions. So we actually do have a poll question. I think this one is probably more worthwhile than the last one. So if we want to throw that up, I'll kind of keep talking as we're doing it. But you can see from the graph here, this blue line is our data set. And these two green lines are the Transmodeler curves. So our data is relatively close in magnitude and variance to the Transmodeler curves. Just a little bit potentially more right leaning than the Transmodeler, so a little bit more conservative. And in Transmodeler, you can define the standard deviation, but in Vissim, it's a fixed standard deviation. So not only is the Vissim default curve shown here in this dotted line more aggressive, it's also this tall spike. So our recommendation really is to try to flatten out the Transmodeler curve slightly by applying a different standard deviation and average, and then just moving the Vissim curve over a little bit because we are not able to modify the standard deviation. But best case scenario is we allow people to be a bit more conservative in how they are, the space they're leaving.
So Adam, the results, just to quick summary, around 70% in the 5 to 10 range, which matches where the bulk of the data is for the data we collected, the blue line, and then some people 10 to 20, a few people in less than 5. And yeah, we did this. There was some difference between, we'll say, between urban and rural values, and so that's why, you know, part of what's reflected on the graph that you're just talking about.
Yeah, yeah, and so I'm showing the urban graph here. We created some rural values as well. Thank you for pointing that out. I'm surprised that no one said they are just bumper to bumper. Surprised and disappointed. So I'll just keep rolling through these. The next one is lane change distance. We just kind of used the trajectory data to get some anecdotal information about lane changes. This one's a little harder to define and is actually typically kind of localized in some form or fashion. So as you're driving, this is really the definition of when you decide to get over or attempt to get over, whether there's another car there and you have to accelerate or decelerate, or kind of wait a second till there's a gap. It's when you start to attempt to do that in order to make a turn that you need to make or take an exit. So that's another poll question we had. Hopefully you guys like doing this interaction. And but
yeah, I've got the poll question up. When do you start trying to get into the correct lane for an exit? Mile, half a mile, quarter mile, less than 1,000 feet, or you just cut right across the gore?
So yeah, I'll just kind of speak as I see these responses coming through. So it seems like everyone in the group is similar to how I drive and how I observe people driving. But for the most part, people are trying to change lanes pretty far in advance, especially if it's on a freeway. Now, if you're on a city street, it might be closer, but there are only 2 people of the people that answered that are saying less than 1,000 feet, and luckily no one's doing this funny option E of the late merge across the gore. But in Vissim, the default value is 600 feet. So if you don't change that, everyone is only going to start changing lanes 600 feet before the exit. So that can create a lot of unnecessary congestion and unrealistic conditions. The Transmodeler curves, as you can see by these 2 green lines, are, I'm going to change the color here, are more conservative, starting at 800 and 1,000 and ramping all the way up to 1,500 for streets and 4,000 for freeways. So our data kind of right now is using the suggestion of keep the Transmodeler defaults as a starting point and kind of move that data into Vissim. So if you're creating a Vissim model, you can now, if you're using 2020 or 2021 versions of Vissim, you can define a distribution. And so this distribution that's in Transmodeler is a great starting point. It causes everybody to start at a greater distance than any of the Vissim defaults. So if you don't have any local data, you don't have any specifics, that's a great starting point. And then you can also supplement that with localized information. So
this is one of the places where we will be able to, as a output, result of what we're doing, is to create, give people that starting point, so that you don't have to do that necessarily yourself, if it's already kind of baked into a file that you're starting from.
Right, preload some base files with that kind of information, as well as this next one, which is the vehicle speeds. So yeah, the speed ranges are just a distribution of speeds for a speed limit. So you can see this Vissim line here is this kind of 3-point curve with little variability. The Transmodeler variability is a little higher, but is more aggressive. On a 70-mile-an-hour road, they have some percentage of people doing between 85 and 95, which is not typical. So not typically that aggressive, I guess, compared to our data, which are these 2 close curves mimicking the same kind of S shape, but a little bit more to the left, so a little bit more conservative and higher variability. So the freeway data is not all that bad for the defaults, but if you look at kind of an arterial roadway, you can see that in Vissim, the only speeds that people are going to vary between is about 44 and 48 miles per hour on a 45-mile-an-hour road. That's not exactly what I experience when I drive a road like this. You see people that are easily doing over 50, and you see a lot of people that are doing 25 to 30. So these curves will provide kind of more data points and a more refined distribution, which creates more realistic passing patterns and platooning on roadways. You don't have everybody just kind of mindlessly falling into this robotic driving rhythm between 44 and 48 miles an hour. You have some variability causing people to need to pass and change lanes and things like that. So again, these would be something that we would be able to create and preload as defaults. And so we've looked at kind of a host of different speed ranges for both urban and rural, as you see on these graphs, for some common speeds. So that was, and that all of those details will be on the handout. I didn't include all the ranges here. It would have created an insane slide. So they should be in the handout that we have at the end. So I'll just kind of move quickly through these last three, and then we'll hit the question. So this one is vehicle fleet. This is really the makeup of vehicles in the model, percentage of cars, trucks, different types of cars. So you can see these navy blue options are passenger cars, but you can see this green is pickups and SUVs. The Kentucky average, based on the VIN data, has a lot of pickups and SUVs as compared to what happens when you just open up Vissim. But it is pretty similar to when you load in the US fleet in Vissim, which is, you can do it, but it's not, when you just open the file, it's not there. So, and then Transmodeler is somewhere between those two. It has a decent representation of passenger cars of middle performance, which might function like a pickup truck or an SUV, but the size and spacing and other attributes might be slightly different. So, so we've kind of developed a range, a set of recommended values, and then some upper and lower limits that we think would be applicable based on the VIN data from Kentucky. So again, this would be something that if you have local data that you can supplement this with, that's always great, but this is just to get us started and moving, instead of having just a bunch of European cars in there if you're using Vissim, or not having kind of the right mix if you're using Transmodeler, although it's closer. So this last one here is the truck weight to power ratio. This one, again, is really only affecting heavy vehicles in the model. You can see there's a bunch of S curves here, which are typical with a bunch of kind of published research and field observations. And the Transmodeler curve is really right here in the middle, this green line. But the Vissim curve, if you can see, this graph's a little busy, is making a reverse S shape, which is really highlighted here. And it has these peaks at the high and low end. So for both Vissim and Transmodeler, we're kind of proposing a line that evens that out. So it evens the distribution of weight and power into more of the middle range for vehicles. And this would likely impact how trucks, heavy vehicles are accelerating and decelerating. A lot of times in Vissim, you see a truck accelerate just as fast or faster than a passenger car. And that's, at least in my experience, not really realistic. So we want to kind of refine that a bit more and load that into the models in a better way. So that was really the 9 parameters. I moved quickly. Hopefully that was a reasonable overview, but in addition, we did kind of review anonymously 15 or 20 different previously submitted models for KYTC projects, and just made some observations about the way people were coding, the parameters that people were or weren't changing. So there's a large amount of variability in the current set of models that have recently been submitted in the last several years. So we're just trying to work together to refine that. So that's kind of where we are today and where we're planning to go in the future. So we're wrapping up phase 2, and as Jay and Rob mentioned, we're kind of moving into phase 3. So that'll be doing some case studies and coordinating with PTV and Caliper, and kind of trying to finalize these parameter ranges and these findings. So we have a handout that we'd like for you to be able to download. I need to figure out exactly how.
I went ahead and shared it.
Okay. Yeah, so if you guys know how to get to the handout portal, you're further along than I am. But if you can get there, you can download that. It's a PDF that has kind of our current draft parameters. So if you're a modeler or someone at your company is a modeler and you'd like to kind of investigate this, we'd love for you to dig into this a little bit with us and give us feedback. Like we want this to be a collaborative effort, so we want to work with people and developing a set of kind of base values that everyone agrees on and thinks are representative of Kentucky. So.
All right, Jay, Rob, Adam, thank you so much. I think we've got enough time here for maybe a couple quick questions. Let's start off with John Callahan. In a microsimulation model, do the parameters get applied to all vehicles so that there is one average vehicle driver per vehicle type? Or is there the ability to assign parameters to, say, 30% of vehicles are older drivers, 40% are young drivers, etc.? Is that too in the weeds for a simulation model?
That's it. I guess I'll take this one if that's okay. That's a great question. I think it depends on what the parameter is. My understanding of how both Vissim and Transmodeler work, when a vehicle comes into the network, it gets randomly assigned attributes based on what it is and what route it's on, the type of vehicle, and the driver attributes. So you can define a distribution, let's say, for headway or acceleration or deceleration, and you can definitely define those distributions in Transmodeler. That they have more parameters that have distribution. So you could try to define that by saying 30% of people will leave this much headway space. Then that accounts for older drivers, and then you have 20% of aggressive drivers leaving this much space. So yes and no, it's randomly assigned, but you can adjust that.
All right, very good. Let's see. Next, Katie Rowe asks, is 8 sample sites considered enough, or will additional study sites be examined?
So I'll field this one, and Jay, Adam, you want to? We had anticipated that we would do more study sites. The events of the spring leading into the summer, traffic volumes decreased really at the wrong time for us. So we were in the process of trying to get more sites. So we have a lot of samples for the 8 sites, and we have we have lots and lots of data, but it is a limited sample size, and so we don't have as much as we'd like. We'll see kind of what happens as we finish up the project. If we are able to get but I will say we did succeed in getting the urban, rural, interrupted and uninterrupted with those 8. So we covered the gamut of what we wanted to get. We just didn't get as much of it as we wanted.
All right, I think we got time for one more. And I think this was a poll question we didn't quite get to, but will you be producing something like a seed file similar to MicroStation, which has the parameters preloaded for Kentucky?
Yes, that is the plan. Yeah, I don't know, Adam, if you want to add on to that.
Yeah, I think that would be my preference. We did have a poll question just asking if that would be helpful. I think I realized that might be rhetorical in a way, but that is what North Carolina does, and they're very kind of prescriptive. They use only Transmodeler, but they have some base files if you are starting from a rural, urban, or mountainous project. And so it would be great to have those same kind of files for Vissim and Transmodeler here that have all this stuff preloaded.
All right, I think we're about out of time. The next session will be starting at 2 o'clock, so I've got to jump over and get that one rolling. But I would like to once again thank our presenters this afternoon, Jay, Rob, and Adam, and give you a virtual round of applause. Yay! Good job, guys.
Thank you, Brian.
Hope everybody found this to be informative. And once again, we're recording all these sessions. They will be made available later. So if you've got a staff member or a coworker who was unable to attend today, these sessions should be available at some point in the near future. So looking forward to speaking with you again, maybe this afternoon, if you're going to be joining some of the other planning track sessions. So have a great afternoon and see you soon, hopefully. Bye-bye.
Okay, thanks everyone.